All right, so we've been introduced to inverses of trigonometric functions. We're going to take it just a little bit further in this video and talk about composition of trigonometric functions. But I first wanted just to review what we have learned about inverses of trig functions. We've learned that the inverse of all 6 of the trig functions are not functions themselves, and the only way that they are functions is if we restrict the domain or limit the quadrants that we access when we're doing inverses. So sine, cosecant, and tangent, just the inverses of those 3 trig functions, are limited to quadrants 1 and 4. So anytime you are asked to find the inverse solution for sine, cosecant, or tangent, you will only be looking in quadrants 1 and 4. Then the inverses of cosine, secant, and cotan are limited to quadrants 1 and 2. So just to reiterate, nothing has changed with the trigonometric functions themselves. It's only their inverses that are restricted to these quadrants. And notice, because they're each restricted to 2 quadrants, one quadrant is the positive ratios and the other quadrant is the negative ratios. So depending on whether the ratio that you are given to find the inverse trig function of, depending on whether it's positive or negative, that will determine to you which quadrant you need to look in. Now let's take a look at the bottom of this particular slide that refers to quadrant 3 as the black forest. We've talked about the fact that if you are referring to any angles in the 4th quadrant based on an inverse trig function, instead of going around the circle through the 3rd quadrant and naming those larger angle measures, whether it's in degrees or radians, rather than doing that, you are actually going to start from 0 and come down clockwise directly into quadrant 4, which means that all of the angle measures that you give will be negative, and they'll be anywhere from 0 to 90 degrees or 0 to pi over 2, negative pi over 2 I should say, and 0 to negative 90. So I just wanted to review that. Now we're going to jump through a couple of things that we've already looked at and get into something new. And this screen looks a little bit crowded, but I want to try to just focus on one problem at the time and point out what they've done and what their arrows are referring to. So let's start with problem number 1 right here. And this is called a composition function. If you'll look right here where they've got f of g of x, you remember in algebra learning about composition of functions. And so it's very similar to that. And you will work from the inside out. So if you look at problem number 1, in the parentheses is asking for the cosine of negative pi over 3. So if you look at your unit circle, negative pi over 3 is right here at 300 degrees or 5 pi over 3. And the cosine of that is going to be the x value. That's going to be this 1/2 right here. So we can rewrite the problem. I'll just rewrite it right above and replace that cosine of negative pi over 3 with a 1/2. All right. Now from there, we need to figure out what angle has a cosine measure of 1/2. So we know we're going to be looking in the first quadrant. Remember, inverse cosine is restricted to first and second quadrant. The first quadrant is for all of the positive ratios, and 1/2 is positive in this situation. So I'm going to look for the angle measure that has a cosine value of 1/2. Remember, cosine is your x value, and we're finding it at 60 degrees or at pi over 3. And the reason we want to write our answer as pi over 3 rather than 60 degrees is because the angle measure that they originally gave us here in parentheses is in radians. So we kind of follow suit with our final answer being in radians. Let's take a look at problem number 2. So we have on the inside of the parentheses the sine of 11 pi over 6. So let's look for 11 pi over 6 on the unit circle, and we find it right here at 330 degrees. And the sine of that is the y value, this negative 1/2. So I'm going to rewrite this as sine, or inverse sine, of negative 1/2. Now I'm looking for the angle where the sine is a negative 1/2. Since this is an inverse problem, I'm limited to the first and fourth quadrants, since this is sine. And the fourth quadrant is where I have all the negative ratios. So since negative 1/2 is a negative ratio, I'm going to look in the fourth quadrant at where my sine is negative 1/2, and it's basically taking me right back to where I was at 330 degrees or 11 pi over 6. But I'm not going to write the answer as 330 or 11 pi over 6 because that would assume that I went all the way around the circle through the black forest to get to that angle. And that's not what we want to do. We want to start at 0 and work down clockwise and have a negative angle. And that angle occurs at negative pi over 6. So that's where that answer is coming from. Let's do a couple more. We have inverse secant of secant at negative pi over 4. So remember, secant is the flip of cosine. So imagine on the unit circle, secant is going to be 1 over x because cosine is just x over 1. So we want to first find the secant of negative pi over 4, and negative pi over 4 is right here where they have a blue arrow pointing. So if we want the secant of that, we've got to take 1 over the cosine, or the x value, which is the square root of 2 over 2. So if I do 1 over the square root of 2 over 2 and flip that, keep, change, flip, I end up with 2 over the square root of 2. And then I have to rationalize that. I'm going to multiply the top and the bottom by the square root of 2. I end up with 2 on the square root of 2 over 2. And those 2's are going to cancel and leave me with just the square root of 2. So now I'm looking for inverse secant of the square root of 2. So now I've got to try to find the angle that has a secant of root 2. And remember, secant, like cosine, is restricted to the first and second quadrants. Since the square root of 2 is positive, I know I'm going to be looking in the first quadrant. So how will I get the square root of 2 with secant? Well, the way I got it a second ago is my x value was root 2 over 2. So it only makes sense that the same thing has to happen now. I've got to find the angle in the first quadrant where my x value is root 2 over 2. 1 over that would give me the square root of 2. So my angle measure is going to be at pi over 4. And again, rather than use degrees, I'm using radians because the original angle that they gave us in parentheses was in radians. And let's look at number 4. We've got the inverse cotan of negative 3 pi over 2. Remember, cotan is the flip of tan, so cotan is x over y. So let's take a look at negative 3 pi over 2 on our unit circle. And negative 3 pi over 2 is actually going to be up here. If you're going in the negative direction, we've got pi over 2, 2 pi over 2, 3 pi over 2, right there. And the arrow is overriding our points, but 0, 1 are the 2 points at 90 degrees, or pi over 2. So what would be the cotan for that? Cotan is x over y, so that would be 0 over 1, which would be 0. So I'm going to put a 0 into the parentheses, since I now have found the cotan of negative 3 pi over 2. Now I'm trying to look for the angle where cotan is equal to 0. Well, if you look at your unit circle between quadrants 1 and 2, 90 degrees or pi over 2 is where you will find a cotan of 0. All right. Let's take a look at this one that I think is the last of its kind. We've got the inverse cosine of the cosine of 5 pi over 4. And 5 pi over 4, let's see it right here. Let's circle it. All right, and the cosine is going to be the x value, which is the negative root 2 over 2. So I'm going to rewrite this as inverse cosine of negative root 2 over 2. Now I'm looking for the inverse cosine of negative root 2 over 2. That means at what angle is the cosine a negative root 2 over 2? Since the inverse of cosine is restricted to quadrants 1 and 2, and this is a negative, we're going to be looking in quadrant 2 for our negative cosine values, and we have that right here. And so that's occurring at 3 pi over 4, or 135 degrees. All right, let's take a look at this problem. What is different? Well, the difference in these 3 problems, 6, 7, and 8, is that now the inverse is in the parentheses. If you go back and look at the previous problems, the inverses were always on the outside of the parentheses. Now we have 3 problems where the inverses are inside of the parentheses. So basically in the parentheses of problem number 6, they're wanting to know what angle measure has a tan of 3/2. Well, since 3/2 does not fall on the unit circle, we really have no idea what angle creates a tangent of 3/2 or 3/2. So what we're going to do is build a triangle the same way that we did when we learned Pythagorean identities in Unit 1. We know that tangent is y over x, so we know the 3 is going to represent y, or the adjacent side. The 2 is going to represent, or excuse me, I'm sorry, the 3 is the opposite side, your y. And the 2 is your adjacent side, your x. And we don't know our hypotenuse. Because 3/2 is positive, we know that we need to build our triangle in the first quadrant. So you can see here from the origin, they've built out a hypotenuse and then drawn a perpendicular down to the x-axis and labeled the y-axis 3 and the x-axis 2. And if you use Pythagorean theorem, you know that 2 squared plus 3 squared, that wasn't really a square, was it? Plus 3 squared is equal to r squared. So you're going to have 4 plus 9 equals r squared. You're going to have 13 is equal to r squared. And so r would have to be the square root of 13. Remember, r is always positive. So you can see that they've placed a square root of 13 on the hypotenuse. And the angle whose tan is equal to 3/2 is right there where I've drawn it, but we still don't know the measure of that angle, but we don't need to know the measure of that angle anymore as long as we have the triangle. Once you have a triangle built, you can find any of the 6 trig functions that you're looking for. And in this problem, they're looking for now the sine of that angle. And all we have to do is look at the triangle to see that the sine is going to be 3 over root 13. And what they've done is go ahead and rationalize that. So I can show you over here what they did. They had 3 over the square root of 13. Then they multiplied the top and the bottom by the square root of 13. And that's how they ended up with a final answer of 3 on the square root of 13 over 13 for number 6. All right, let's take a look at number 7. And same situation, you have the inverse on the inside of the parentheses, so we need to build a triangle. Inverse cosine exists in the first and second quadrants. Since this is a negative, we know we need to draw our triangle in the second quadrant. So I'll go ahead and draw it out here and then drop the perpendicular. So the -5 is going to be my x value, and the radius, I'll put it right here, is going to be 13, and we need to use the Pythagorean theorem to identify the y value. So we take -5, we square that, plus y squared is equal to 13 squared. 25 plus y squared is equal to 169. And better do this on my calculator to make sure I get it right. 169 minus 25 gives me a y squared equal to 144. Square root both sides, y is going to be 12. So that'll be my y value. All right, so here's the angle that we were trying to identify that has a cosine of -5/13. We still don't know the angle measure, but that doesn't matter. We have the triangle built. We can now find the tangent of that triangle. Tangent is going to be y over x, so that's going to be 12 over -5. We'll put the negative up top with the 12. So that gives you a couple of problems that you can look at and work from. We've done a scavenger hunt. I've posted that online. You might want to pull up this scavenger hunt. The nice thing about it is that once you work a problem, you can scroll through and find the answer up top. These are the answers here, and it gives you the next problem that you can work. So these are some great problems to practice, and it really gives you a good feel for going back and forth between taking trig functions and inverse trig functions.